Okay, what I have here is a plot showing the potential energy curve for a pair of hydrogen atoms. Okay, so H2 molecule. So you have a hydrogen atom here and another hydrogen atom here. We're going to treat, remember, hydrogen as a one proton and one electron going around the proton, right? So we're just going to treat the whole atom, the proton and the electron together as one particle. And so we're going to define the distance between the two atoms as r. So we're going to plot versus r here. R in picometers. This picometers is 10 to the negative 12 meters. And we're making a plot of potential energy as a function of r. So this v of r here, that's like f of x. Okay, we're not multiplying v and r. That's v as potential energy as a function of r. Okay, so this red curve right here is your potential energy as a function of distance between the two hydrogen atoms. Okay, so let's try to interpret what this means. Let's consider the scenario where the total energy is the blue line. So if this is your total, so this E total is going to be equal to what? Kinetic plus potential. So let's see what happens. So this diagram right here is a very convenient way of summarizing how the two atoms would interact. How would they move relative to each other? Okay, so let's see what happens here. So you have your total energy is the blue line, and the red curve is potential energy. Okay, so this potential energy curve right here summarizes how the two atoms would interact. So let's imagine when they're very far apart. And in this case, what happens to this red line? Remember we said when they're very far apart, this red line eventually approaches zero. So there's my zero right there of my scale, right? Okay. So you'll notice that the total energy is above zero, right? So when they're very far apart, okay, the potential energy is hardly changing right here. This hardly changes over here. It's almost close to zero, right? So you can say that when they're very far apart, so let's make a list here of things. Okay, when R is very large, okay, your potential energy is essentially zero. It's constant, right? So I want to have these two wiggly lines. It's like approximately equal. Okay, so potential energy is approximately constant. And so if potential energy is constant and total energy is also constant, remember, okay, and potential. So what happens to your speed then? Kinetic energy. Kinetic energy is also constant. So in other words, it's like they don't really care about each other. They're so far away from each other, they don't interact. So they're not going to affect each other's motion. So for practical purposes, we say the kinetic energy of the two is essentially constant. Right? So that's when they're very far apart. Now what happens when they get closer? Let's say they're already at this distance. So they're approaching each other, right? Let's say at this distance right here, at 200 picometers. Look what happened compared to before when they were very far apart. What happened to the potential energy as they approach? Potential energy drops, right? So as R decreases, as they approach each other, then your potential energy is dropping. What happens to kinetic energy? The potential energy is dropping. Total energy is constant. Okay? Potential is dropping. What's happening to the kinetic? Increasing. What? That's what it is on the graph. There's no plot on the graph for kinetic energy. What you have on the graph is just the total and the potential. So this difference right here, let me find another color. I'll just use black. This difference right here between the total and the potential, that difference is your kinetic energy. Okay? So your kinetic energy has increased. So in other words, now they start to see each other, they start to feel attractions for each other. That's why they're speeding up. Okay? If they're repelling each other, they're not going to speed up, right? So what that means is when the potential energy is dropping, the kinetic energy is increasing, that means they're accelerating. Force equals mass times acceleration, you recall from your early science courses, right? So they're speeding towards each other, that means there's a force between them. There's an attractive force. Where does that attractive force come from? Well, remember your atom has a proton and an electron, right? So you have a proton here and an electron here. The other atom also has a proton and an electron, okay? So you have electromagnetic forces of interaction. Your proton here would be attracted to that proton would be attracted to that electron. Of course, the protons would also repel each other, the electrons would repel each other. But if the atoms behave this way, then it must be that these attractive forces are stronger than the repulsive forces at this particular distance. Okay? What happens if they keep moving close? So they keep moving closer together, they're going to speed up. So at around 100 picometers right here, what's happening now? Potential energy has dropped significantly, and kinetic energy is really high now, right? So they're really much faster now. Okay? So that's what happens. There's attractive forces that getting them to speed up as they approach towards each other. What happens when you reach this bottom of the curve right here? This is around 74 picometers for hydrogen. You don't have to memorize these numbers. This is just, the purpose of this lesson is just to illustrate to you how two atoms would interact. Okay? So, what happens at the bottom here? Then that's where they're able to achieve maximum kinetic energy. Okay, so this 74 picometers, we generally refer to that as R sub E, the equilibrium internuclear distance. Okay, so at R equals R sub E. Okay, V is minimized, K is maximized. Right, maximum speed, maximum kinetic energy. Okay, so actually what happens there is you have a balance of attractive and repulsive forces, because what happens as they continue moving closer, once you get below 74 picometers, what do you get? Let me just clear up the screen now. My ink. What happens once you're past the 74? Let's say you're over here at maybe 70. You pass the minimum in your potential. What happens to the potential? It increases. So at R less than RE, your potential energy starts to rise and your kinetic energy starts to drop. They start to slow down. They're getting too close for comfort. They're starting to repel each other. So that means the repulsive forces are now predominating over the attractive forces. Okay? And why would that be? Because now your charged particles are getting way too close to each other. The protons are too close to each other, the electrons are too close to each other. So now the repulsive forces are bigger than the attractive forces, so they slow down. Okay? So what happens eventually? When you get to this point over here, where the total energy is equal to kinetic energy, whatever that distance is, your total energy at that point is equal to kinetic energy. What does that mean about it's equal to potential energy, right? Where the red and the blue line intersects, the same value for potential and total. So if potential and total are the same, what's the value of the kinetic energy? 0. What does 0 kinetic energy mean? 0 kinetic energy means 1/2 mv squared is 0. Mass is not 0. Mass is not 0. So if the kinetic energy is 0, what does that mean? V is, what does 0 speed means? Stop, right? Not moving. So they're approaching each other. So what happens here? They're approaching each other. Initially, they move about more or less at constant speed, right? As they approach. And then they start to speed up. They reach maximum speed at RE. And then past RE, they start to slow down because of repulsions. Eventually, they get too close for comfort. You get really close. You'll notice here the potential energy at short distances rises really sharply, right? As you go closer, once they get to the point here, they actually stop. And we say, then they're not going to get any closer than that. You cannot have total energy less than the potential, right? So they can't get any closer than that. So that's where they stop, but they're still repelling each other, so what happens then? Then they start to separate. they move apart. So once they reach that point, they spread out, they separate again, and then as they separate, what happens to your potential energy when they separate? Potential energy drops, your kinetic energy will be increasing. So they're going to start speeding up again. And then they're going to reach maximum speed when they're at this distance. So they're not moving that way. And then once past RE, they're going to start to slow down, slow down, slow down. Kinetic energy is dropping. Eventually, they move at constant speed, separate from each other, never to see each other again, unless they get bounced back from a wall or something. So those two hydrogen atoms, if they were separated to begin with, they're not going to get stuck. Okay, they're going to collide and then they separate. They're not going to form an H2 molecule. They have enough energy to separate. Okay, now let's see what happens if, let's say, somehow while they were close by here, okay, over here at this distance, let's say, a third atom comes along and takes energy away from them. So the third atom collides with them, like let's say they're near a wall, for example. Okay, when that happens. And then a third atom carries energy away from them. So the total energy now drops to this green line right here. What's going to happen? Okay, let's see what happens then. Well, if the total energy is represented by the green line, okay, first of all, if this is the total energy, is it possible for them to be separated by this distance? Well, let's take a look at this. Okay, this is my potential energy. I'm sorry, that's my total energy, right? The green line is my total energy. And my potential energy is this one, right? So total energy is potential plus kinetic. So let's say my total energy is, let's say this, let's just make up some numbers. Let's say you can see E is bigger than E, right? So let's say this was 10 and this was 3. What would be my kinetic energy? Negative 7, right? 10 minus 3, negative 13, right? Negative 13 plus 3 would be 10. So when potential is less than total, that means a negative kinetic energy. Well, can kinetic energy be negative? Let's look at the formula for kinetic energy. 1/2 mv squared. M is always a positive number. Mass is a positive number. You square something, it's always going to be positive, even if it's unless it's imaginary, right? So that means, in reality, you can't have a negative speed. You can have negative velocity, but not because of direction, but negative speed you can't have. So this is impossible. So what we say then is all of these cases, all of these distances where the potential energy, so if this is your total energy, okay, this distances right here is forbidden. You can say it's classically forbidden. And it's called classically forbidden because in modern theory, there's actually a finite possibility that that's going to happen. But using just plain old classical physics, okay, the ones that you learn, Newton's laws and all that, this is not possible. So they cannot stay far apart, farther from each other than this distance. Okay, so this distance right here, this is as far away from each other as they can get. And this distance right here, over here also your potential energy is also also higher than the total, right? So this distance right here is as close as they can get. Okay? So this distance right here is classically forbidden. This distance here, less than this distance here, is also forbidden. So what happens to the two atoms? The distance between them is just going to go back and forth between these two possible distances. Okay? So within this interval. So what ends up happening is your atoms will just be vibrating about this distance right here. So they're going to get close. So let's call this L, and let's call this distance R. Okay, so this L right here would be your left turning point. That's as close as they can get. Okay, remember, when potential is equal to total, then the kinetic energy is 0. They stop there. They have to turn around, speed up. Okay, so they speed up, slow down, stop. And then they go back, speed up, slow down, stop, speed up, slow down, stop. So your molecule, your two atoms are stuck. That's how you form a molecule. When the atoms don't have enough energy to separate from each other, you say you have a bond between them. That's how a bond is formed. Okay? So, that's when you get an H2 molecule. So in order for two hydrogen atoms that were separated to begin with, in order for them to get stuck to form a molecule, there has to be a third body that takes away the energy from them. Okay?